every force there's an equal and opposite force. So the amount of force it takes.
But what is the force?
The car going forward.
But the mass
Then the acceleration.
Yeah, what's
and then
triggering the force?
The spring inside the car.
Here at Arcade Middle School in Sacramento, California, 8th graders Josh and Rex are trying to figure out how adding extra weight to a spring-loaded car will affect the speed of the car.
Then what's the mass of it? The spring, the mass of the spring, times the acceleration of the spring equals the force?
What do you think?
I didn't think it was anything. I just listened to what you said and I put up a good argument.
Kids arguing about science warms the heart of teacher Vicky Velasco. She's teaching Newton's laws in a new way, through argument writing.
Good scientists have to be good writers, and they have to be able to share what it is that they're trying to claim is true. This is the real deal, folks. We are gearing these kids up to be scientists, and that's what we want. Hey, welcome, this is my classroom.
Ms. Velasco is working with Tanya Baker of the National Writing Project to help kids learn how to make scientific arguments in writing.
Yeah!
Yes!
Woo!
I think writing allows us to deepen the intellectual rigor and help kids really deepen their understanding and feel mastery and feel powerful in the discipline.
For their next assignment, Vicky's students will conduct 10 different experiments over the course of the next 2 days. After that, they'll need to make an argument in writing.
So at the end of this 2-day adventure, we are going to have to make a claim. And that claim is going to be which one of those particular activities best demonstrates Newton's 3 laws. What is going to need to be in that writing to make it a good, solid claim?
You need evidence and reasoning to make sure the claim is actually correct.
Good. What would be?
We're going to be watching 2 preliminary steps in this challenging writing assignment. We'll see the students make observations about the experiments, and then we'll see them use reasoning to support their claims about each experiment. Which of Newton's laws does each experiment demonstrate?
Where does it look like that ball bearing is going to end up, Bailey? Right where the cup is.
There are a couple of things that Ms. Velasco does to help her students make careful observations. Before they run the experiments, they draw the setup.
What I'd like you to do is I'd like you to draw a free body diagram. It does not need to be pretty.
Drawing the objects and the forces acting upon them can help students observe the results more clearly. And then comes the demonstration.
All right, you ready? 1, 2, 3. Woo! Thank you. So now observe. Write them down. I'm not going to do it again because that will definitely mess that up, you know? Write it quietly. What types of things did you witness occurring?
Now the students will practice making observations. It's not as easy as you might think.
All right, so tell me one piece of good evidence that you witnessed. What did you see?
So, like, with Newton's first law, you moved the stick out so quickly, and the ball wasn't very well inside of that cup. So because of that, the ball stayed in place while everything moved. And because of that, the cup went right to where the ball was, and the ball fell.
Okay, so back up just a little bit. Explain to me what are you saying your evidence is? What is the piece of evidence that we're looking at?
So that, like, the ball couldn't have gone into that if it was going slowly.
Okay, but now you're pushing into reasoning. So just tell me, what are you absolutely seeing with your eyes happen?
The ball landed in the cup.
The ball went straight down into the cup. Perfect. That is a perfect piece of evidence. So
We saw her ask students to make observations. And because they were familiar with Newton's laws and because they could name Newton's laws, they would say things like, I saw inertia, or I saw gravity. And what's really interesting is when you ask them to step back and say, well, what did you see? You know, how does that demonstrate what you know about gravity? You could see them recognize that there might be a lack of depth to their thinking at this moment.
It's Newton's first law, an object at rest wants to stay at rest.
You think you understand it, but when you have to write it down, actually think about it, you realize that you don't understand it as well as you thought.
Ms. Velasco and Zion help clarify what an observation is.
If I pick up this book and I drop it, what would be an observation there? What do you...
That the book dropped.
Book dropped. That the book fell. What you actually can see.
Once they have their observations recorded, Ms. Velasco asks the students to use reasoning to figure out which of Newton's 3 laws is reflected in each experiment.
So yeah, okay, so I
Every
think it's the
action
third law.
has a reaction.
Oh yeah,
So
yes.
it's the third law.
The third law, because of the opposite and equal reaction.
It could be the first law because without any movement it would do anything.
Oh yeah, true, because it needed an outside force.
So
to
without
start
like
it,
flicking
so it
your
could
wrist, it doesn't move.
Talking with classmates is often helpful, but reasoning from evidence can be tough. Here students are trying to figure out why it should be easier to catch multiple pennies resting on their elbow as opposed to one. To help, Ms. Velasco asks questions. Lots and lots of questions.
And then, so if we're talking about Newton's first law, what about the question, is it getting easier as I stack more pennies or is it getting harder?
It's getting harder because you're using one hand and there's more pennies, so it's harder to grab all of them.
Okay, so the technical skill needed to grab all of them, but what about the mass? What's happening to the mass as I add more pennies? Okay, but are the pennies really affecting your arm that much as they move? No. So what is happening to the inertia of the pennies as I keep... Well, I think it falls the same because, right, gravity is acting on everything the same, but is it going to fall more straight down? Does it have more inertia or less inertia as I add? So there's less inertia as I add more mass? So an object that like is a boulder has less inertia than a ping pong ball. A boulder wants to move more quickly than a ping pong ball does if I force it. So if I push a boulder and I push a ping pong ball, it's easier for me to push a boulder? No. Okay. So if it's not easier for me to push a boulder, as I add more mass, what does the inertia do? Does it increase or decrease? Is it easier to push it or harder? It's harder, so inertia increases. So as we add more pennies, inertia increases. Those pennies want to stay in position even more. So it should actually get easier to catch them. I get students to give me more by asking questions and by having them come up with questions. I think of my job as sort of like prying the door open a little bit so that they can push their way through and get real understanding. You're saying that it's
The third
law.
He was saying it was the second law, and I didn't
Okay,
understand
so why
that.
are you saying it's the second law?
I was saying it's the second law because the math.
And as she nudges them along, she's also conducting informal assessment.
Correct. It is easy to informally assess students along the journey and see where they may have disconnected with their reasoning. And so because it sort of diagrams out the learning process for me, it's easy for me to see where that disconnect happened and then get them back on the right path.
With 10 different experiments in this assignment, the students get plenty of practice. 10 chances to make observations and 10 chances to try making a reasoned argument.
Both pigs were applying the same amount of force and pressure, and they have the same mass. And because they were pulling on each other with the same amount of force, they would stay in the same spot because they canceled out the net force.
We often see teachers take a big idea and lay out a big assignment to get at the big idea. The thing is, if you get lost somewhere along the way and nobody realizes you're lost, by the time you get to the end, you might fail to understand a really key idea. And in this series of 10 short demonstrations, allow kids lots and lots of chances to practice. And so they can just have fun. It's a really relaxed atmosphere, and kids are getting better and better as they go along.
An object at rest wants to stay at rest, so they're not going to move unless you turn them on.
At the end of the 2 days of experiments, the payoff of that practice is clear.
What happened in the lab was when we added the 100 milligram weight, or the gram weight, it slowed down, but no matter how far you pulled it back, it didn't speed back up, it just stayed at the same acceleration as when you first added that mass.
And if you wait a while, like while the 100 gram weight is in the car, you'll see the car speeding up, as it goes farther along the table.
We saw Vicky's kids today practicing over and over again. I observed that is connected to Newton's law. Through my reasoning, I'm going to reason a connection. Practicing that again and again and again. That's practicing writing, though they did it orally. It's really practicing the composition of this thought process, which they're going to have to do in writing at the end.
Okay, ready? On your marks. Get set. Go! I'm really excited about this new way of getting kids to really think about the answer and not telling them the answer. That's no longer it. It's not a lab to get one set answer. They have to fight for it. All right. Thank you, Bailey. Thank you.